No, we talked about forces. Now we're talking about electrical potential energy. And, what does potential energy mean? Well, it doesn't mean that different than gravitational potential energy. If I look at, this system here, imagine I've got a ton of this looks like a parallel plate apparatus to me. And I put some little charge right here. Well, it's got a lot of potential energy. It's got potential to speed up and have kinetic energy, right? There's two types of energy, potential and kinetic. In this case, instead of gravitational potential, we're only dealing with electric potential. And by the way, as we get through this unit and we do apply conservation of energy, we never concern ourselves with gravitational potential because, again, it's negligible compared to electric energy. But again, how it's similar then. So if I had, excuse me, some mass at the top of a tower, right, it's got lots of potential energy, and as it drops, its potential energy becomes kinetic energy, right? And at the bottom, it doesn't have potential energy anymore, at least gravitational potential, because it's already down at the bottom, right? I have to lift it back up and give it potential energy. So potential energy. So a positive charge located near other positive charges has high potential energy, or a negative close to negative charges, by the way. But as this thing is allowed to lose, it loses electric potential as it comes near here, because once it gets to this negative charge, if I had a positive charge sitting right here, it's got no electrical potential because it's happy. It's not going anywhere. It's not going to move anywhere. But what does happen is it gains kinetic, because as it moves through here, it accelerates, right? It goes faster and faster and faster till it gets to this point, and then it doesn't move at all. Just like an object speeding up as it comes to the ground, right? And then it doesn't move at all. Okay, so just recap: electric force and gravitational force. There's the formulas. Potential energy. Remember gravitational potential energy from just recently, our mini unit? Well, if this is gravitational potential energy, think about, just look ahead to the next slide, but think about, what is electrical potential energy? And it is the same, except no negative. And the reason is the negative, you could think of, I never mentioned this during that unit, but you could think of that negative with the gravitational potential energy in general as referring to an attraction, right? If you stuck some object around Earth somewhere, it would have a negative gravitational potential energy and it would be attracted towards the Earth, and that negative sort of reflects that. Well, with electric energy, it's kind of the same. If you have two oppositely charged objects, here you keep the negative sign in if it's negative in the charge, then the electric energy ends up being negative, and it's like they're attracted to each other. But if you have two of the same charge, then you end up with a positive electric energy, and that means they repel each other. Okay? There's another term that we don't use, we don't have a gravity equivalent to, and that's electric potential. And V, volts, you've seen this term lots of times. We just say it's potential energy per unit charge, and it's a pretty useful term, you'll see. We give it units, the symbol V, and we also have units V, but sometimes we call it joules per coulomb, because it's joules energy per unit charge. And similar to the electrical potential energy, if there's a negative in the Q, if the Q is negative, then the potential energy is negative. And again, that means that, if I've got some positive charge, it's how much energy one positive coulomb of charge would feel in a certain location. Yeah, things that make you go, huh? Why keep the negative? I hope I covered this, but we keep the negative because negative means that you have an attraction, an attractive force, and a positive means that there's a repulsion. Okay, and that's all it means. It doesn't really mean anything that you can picture or anything with them. It just means is there attraction or repulsion. Okay, so a little example. Electric potential at a distance 0.5 meters away from a point charge is 45,000 volts. So what this means is, if I stuck 1 coulomb of charge right here, it would have an electric potential, it wouldn't feel, I guess, but it would have an electric potential energy of 45,000 joules, positive. So determine the sign and magnitude of the point charge. So everything's positive here, so you don't change any of the signs in here. So my Q must be positive. Okay, and what that means is that the positive refers to, again, the fact that if I stuck positive 1 coulomb here, it would feel 45,000, it would have, not feel, positive 45,000 joules of energy. And that positive refers to the fact that it's a repulsive force that it would be experienced, not an attraction force. Often we use the term potential difference. You might have heard that before, and it just means, you know, if I have this location B and this location A, and it's in some sort of electric field, it's the difference in potential energy that it would have between here and here. So it's just comparing two locations. And you can also say it's equal to the work. So if I have, if I had a positive charge and I had to move it from A to B, how much work would I have to do? And first of all, you got to think to yourself, would you have to work at all? Because it would want to fly out because of this, and that of course means it would be a negative number. But, so potential difference is just change in electrical potential energy divided by Q, and then you can rearrange that to have this equation. So here's a little example. If it takes that much work is like change in energy, okay, so that's my change in E, to move that Q of charge from point to X to Y, I want to find the potential difference between those locations. Okay, so I'm looking for potential differences delta V right here, okay, and actually this is the equation I use, right, because delta V is what I'm looking for. Change in E is the work, because work equals change in energy, and there's my Q. So it's actually pretty simple. So simple I never actually did it. Okay, so the way you would do this, I better write it out though. So V then, and it's change in V, will equal 0.0012 divided by the 4.4 times 10 by 6. Okay. It is important that I put the triangle there, by the way. So change in V is that, and you can work out what that is, and the answer would be joules per coulomb. Okay. Okay, so going back to parallel plates, because we're going to do some calculations related, we say the field strength is constant, and the net force within them would be constant for any given charged object. So the net force here, it's saying it doesn't change. As my electric charge moves towards the positive charge, the net force it feels at any one point would be exactly the same. With the exception of bunching, field lines are straight, and they go from positive to negative. To find the field strength between any two parallel plates, given a potential difference, this is how you find it. Okay, so this, by the way, is something that goes on your formula sheet in the special section just for parallel plates. This is not a common equation. It's only true because you have a uniform field. Okay? And R is plate separation. So this, is obviously some animation I found, but it doesn't use the right symbols. So let's just use my equation, okay? The potential difference across a parallel plate apparatus with separation, so R of 0.03, determine the field strength. And we're given our delta V. So you just substitute in, you get 47,000, and remember that A and B are going to be the same. It doesn't change. Field strength is constant, okay, throughout the plates. Okay, I'm going to stop this video right here and make a part 2.